Howdy. The purpose of this video is to talk about the difference between elastic and plastic deformation. We're going to talk about this at the macroscopic scale now, and we're also going to look and see what it means in terms of a stress-strain diagram, especially when we load and unload a material. Okay, so you've encountered elastic and plastic deformation before. When you think of elastic deformation, think of something like a spring. So this is something where you can deform it, but when you release that stress, it'll pop back to the original shape. So all of that strain has been totally recovered. If there's no permanent deformation, then that was elastic strain. Think about something else where you're actually bending a metal and maybe it doesn't pop back, right? So bending a spoon, for example. This would be plastic deformation. We have induced some strain in the material. In this case, it's a bending strain. It could be tensile. We could be pulling it. Or it could be compressive. We could be compressing it along one axis. But in all of these cases, when I remove the stress, if there's a permanent deformation, that's called plastic strain. Let's look at a quick demonstration now. This is a paperclip. You've seen one of these before. If I apply some initial stress, this is not a lot of stress, I've changed the shape, but when I remove that stress, it bounces back to the original shape. So this would be an example of elastic strain. If I apply a larger deformation and I let it go, I've opened the gap somewhat. So there's an additional strain that was not recovered when I released the applied stress. And that's what I call the plastic deformation. Now, something that's important to note is that there can be components of both elastic and plastic deformation. So let's do this again. This is our initial shape. I will apply some stress, a fairly large stress, and when I let go, it does bounce back a little bit, so we're recovering that elastic component, but there is still some overall residual strain. So there was both an elastic component that the shape was recovered, and there is a permanent deformation, and that's what I call the plastic deformation, or the plastic strain. So what does this look like on a stress-strain diagram? We've talked about these before, and we see that there is an initial component that we call the elastic region. And if I apply some stress, and then I remove the stress in this region, all of that strain is recovered. So usually this region is fairly linear, and it ends somewhere. And so we talked about yield stress, yield strain before, but the yield stress is where we've started to undergo permanent or plastic deformation. So as long as I stress that material to somewhere below the yield stress, as I've defined it, when I remove that stress, I come back to 0 on the strain curve. So there's no residual deformation. Now what happens if we apply greater stress past the yield stress? Let's come somewhere out here. So this is some stress, and that stress is greater than the yield stress in the material. Now I've undergone some plastic, some permanent deformation. So when I remove the stress, what I do on a stress-strain diagram is I follow back the original slope of the stress-strain curve. So I take this stress-strain slope, and this is the slope gives us the elastic modulus. I mirror that, I bring it over here, and I follow that same slope back. And so what I'm doing is I'm illustrating how I recover the elastic component of the strain. So I can see when I applied the stress originally, I came out to this point. And so my deformation at that point was, we'll call it epsilon 1, strain 1. When I removed that stress, I come back to some other point, strain 2. So what are these different parts? The distance from 0 to this strain 2, that's the permanent deformation that the material has undergone. So I would call that the plastic strain, the plastic deformation. This part here, the difference between strain 1 and strain 2 that was elastically recovered, that's the elastic strain in the system. And we see this in real data. So this is an example from a nano pillar. I believe it might have been a metallic glass. But what you can see is that we have very linear behavior initially. the yield stress is somewhere up here for this material. Once we go past that, we have some plastic deformation, but it still recovers elastically. And so you see that these slopes exactly mirror that initial slope. So this is the elastic recovery. So for example, in this red curve, the plastic deformation would be this distance, and the elastic recovery, in this case, is much larger. So what happens then? If we load the material again, we now have a new starting point, right? Because we've had some permanent deformation. We never go back to the origin. So if I was to stress that material again, I'm now basically on a new curve. And so as long as I stay at some small stress values, this curve would behave elastically. So I could follow it up and come back down. If I go to yet a higher stress, I've now added some additional plastic deformation. And so in this case, this would be the blue case. I've gone to a higher stress. I release that stress. Now I have a secondary plastic deformation. And I can do that again. Look at this green curve. Again, I'm stressing it to an even higher stress, so I've now added additional plastic deformation. So this would be an example of cumulative loading and unloading. Each time I load it, if I load it to a higher stress, I've added some additional plastic strain. And as you can see, our new starting point essentially keeps going to higher and higher strain values, because once I've plastically deformed that material, I don't get back to the original undeformed shape. Okay, so I did want to look at one other example, and this could be very similar to that last case. So I'm going to start at the origin. I'm going to apply some stress that's over the yield stress. So let's call that sigma prime. And I will remove that stress. So again, I come down, I follow that same initial slope. You'll have to apologize me if my lines are not, you'll have to forgive me if my lines are not exactly parallel. But what I want you to notice now is, what is the new yield stress of this material? And remember, the yield stress is defined as the stress at which we're going from elastic to plastic deformation. So originally, my yield stress was somewhere around here. But now I've changed the system, right? I've undergone some permanent deformation. And so my new yield stress tends to be at a higher value. So I'll call that yield stress number 2. And oftentimes, the curve is not perfect. You know, there's a little bit of an additional add-on that you might see. But the point is that after I've undergone some plastic deformation, the yield stress of the material is now greater than what it was originally. Okay, so in this video, we've defined the difference between plastic and elastic behavior, and we followed that deformation history and looked at some cumulative loading and unloading cycles in one example case.